So welcome to the second class. So last time we overviewed syllabus, and today we will essentially introduce the topics and give you the basic flavor. Why are we doing why do you need to take the class like this? So the class is named Formation and Solution for Geosystems Engineering Problems. It could be really named Introduction to Numerical Methods. What we're actually going through here in the course is very similar for all other engineering departments, so everybody kind of has to go through something like this. It's just that some of the problems that we will be presenting will be specific for petroleum engineering a little more than they would in a different department. Some problems will actually be common to, for instance, civil engineering. So civil or chemical engineering. So it's going to be a mix. We're going to try to introduce where are you going to use the methods that we're mentioning in your further education. So course topics I already mentioned last time. So first we will just do introduction, and we will go through linear algebra review because most likely than not you have not had it, and this is sort of a mathematical part that we need for handling matrices and arrays. Then we will actually spend some time with introducing you to programming. So there is no assumption that you know programming from somewhere else. We are starting from scratch, and we will use programming environment called MATLAB. So we will go through MATLAB fundamentals. How do I type in arrays, numbers? How do I display things in MATLAB? Things like those. Then elements of programming that are essentially same as in any other programming language. It doesn't have to be MATLAB. And how do I find errors and basically weed them out of my code, which is called debugging. There will be also mention of the errors in the sense of those that are not necessarily due to you typing them in, but simply numerical methods carry certain error with them, and we will look into those as well. And then we will actually start with numerical methods. First topic will be root finding, basically more complex way to find roots of so if you have quadratic equation, you know the roots, but in all other cases you need help for some function that is more complicated than quadratic. Then we will go into systems of linear equations, which is really the core of the course, and they underlie most of the numerical methods out there that are of practical interest in engineering. Curve fitting, something that you will do a lot, especially when presented with data. In petroleum engineering, we are often presented with data. We don't necessarily know the background of the data, so first thing that you do to kind of just to process what the data is, you try to fit a curve to a bunch of points to see any trends. And curve fitting, we will actually figure out how that is done. And then we will move on what I call numerical calculus, some elements of how do I do differentiating and integrating in numerically without having analytical solutions. And we will go over simple ways to deal with ordinary differential equations. So if you're already now taking differential equations, this will really come by the end of the course, so you will already be a specialist in analytical solutions to differential equations, and I'll show you how to do numerical solutions. All right. So I already mentioned that I will be posting all of the course materials. That includes any PowerPoints, handouts, and codes, and I will also post the video. Textbook is optional. This first one is our main textbook. There's an alternative. Both can be found in the reading room if you need them. You're not required to purchase the textbook. You can make do with whatever I post in class. Software will be MATLAB. You can go ahead and install it for yourself, but I will remind you again, we will probably take a week or so to get to actually using MATLAB because we will go through the linear algebra review first. So here you can actually, it's a free installation for any UT students, so you can just follow the instructions on the link that is posted. You do need to use it or set up your account using an email address that is affiliated with University of Texas. Once we get to actually, you will not necessarily use calculator as much in class. For that, you can actually use MATLAB, but it's a fancy calculator on your computer. But once we actually get to having an exam, you will not be able to use a graphing or programmable calculator. So for exam, you need like one of those basic $10 things. Okay, some very basic calculator. Right? There will be a lot of, if you do installation yourself, there will be a whole lot of toolboxes that are optional to you. We won't need most of them here, but if you have space on your computer, just install them all and you will have them for later. So it's up to you really. We can just do with the basic MATLAB, and maybe image processing toolbox could be helpful depending on what type of project I decide for you to do at the end of the course, which I don't know right now. And if you're actually doing calculus, then you might want to, or you want to use MATLAB to do calculus symbolically without numerical computation, then you might want to install symbolic toolbox and kind of check it out. So those are my suggestions, but this is really up to you. How much space you have on your computer, and if you want to make sure that you can use it later. All right. So I'm gonna, before introducing actual topics, I'm gonna actually motivate why do we need computation? What is computation? So why do we need computation in engineering, and what is the importance relative to all of the things that you have been so far introduced? And I'm going to start with the sort of a classical joke, even if it's a little nerdy. So if we have a scientist and engineer in the quest for knowledge, so scientists in general, oh, joke is actually coming a little later. So scientists, they seek to understand the nature in sort of like very fundamental processes. How do they work? If I have certain setting, what can I expect to have based on the circumstances and forces that are at play? And that can be very simple. Now, if I'm an engineer, what is the fundamental difference with respect to a scientist? You seek to apply. So the way I like, that's a very good way to put it, but the way I look at it is you're not necessarily picking what you're going to solve fundamentally. You're given a set of circumstances. You cannot sit in the lab. You cannot do petroleum engineering in the lab for long. You can do some fundamental investigation, but if you're going to be a petroleum engineer, you have to go to the field. In the field, you're given what Mother Earth has given to you, so you cannot necessarily pick what are you going to isolate and study. You basically have to deal with the nature as is and just apply and get a solution, even if it's sometimes a quick solution. Okay? So often you will actually, in engineering, you might actually act just based on your best guess, educated guess, and see what happens without often understanding the very basics. Okay? And then you'll go back and try to understand the very basic science beneath it. Okay? So it's basically a more practical science. So engineers, they design and build things simply to work with the nature as given. And they also often have to first figure out what is the most, in order to be an effective designer of whatever tool that you're designing, you have to figure out, okay, what is the most important thing at play here? Okay? If I'm in the field in petroleum engineering, is gravity the most important force affecting my fluids? Do I have gravity drainage happening? Are the maybe capillary forces more dominant in the situation that I'm working on? And based on the answer, you're going to have, basically you're going to design your tool. So often you have to be able to simplify and predict some sort of general behavior without going into too much detail. And also a comment is that out of all of the engineering fields, petroleum engineers deal with some of the most extreme situations. Say for going to the moon, you actually have some most extreme situations at hand. If you're an electrical engineer, you actually, or chemical engineer, you're building something that is right in front of you. You can design your system. Okay? If I'm designing a chemical engineering plant, I'm designing it myself, so I can place the reactors and optimize them at will. Okay? Whereas in environmental engineering, they already have to deal with the soil as is in the given region and try to fix it up. And petroleum engineers can't figure out, don't deal with soil, that's not deep enough, right? You actually have to go even below. The moment you go going deeper, the pressures are higher, the temperatures are higher. You don't have like any tools that you're sending down a hole. They're not the tools that are working in at room temperature. Okay. What is the gradient of temperature? If I go down 1 kilometer, how warmer do I get? 23. So at 3 kilometers, I'm 96 degrees above what it is on surface. Everything changes. Right? So those are the extreme, and then what is the gradient for pressure? You can do psi per foot or megapascals per kilometer. Certain numbers that are used. That's for water. Entire rock, 23. So it's actually close to the Celsius degrees as well. So basically, you're going to go 23 megapascals per kilometer or 1 psi per foot. So 1 psi per foot is easier to remember. So basically, you're going to imagine the weight. So all of your tools, anything that you send down holes has to withstand that. And of course, all of that pressure and temperature has an effect on the formations as well. So that's something that's just simply given, so we cannot necessarily avoid how complicated subsurface systems are. All right. And then in terms of, so there's science and engineering that has traditionally been the case, but most recently with the advent of computers, there's also computation as the third leg of science. And I'm not gonna, this is a very short movie, but I'm not gonna spend time on it now. You can watch Dr. Oden, who is one of the famous computational scientists here in Austin from Institute for Computational and Engineering Science, explain how it is important. But basically, computation or solving numerically problems over large domains has become the third leg of our quest for knowledge. So basically, you can have theory, you can have experiments in the lab, and you can have computational experiments, or basically solving things numerically on a computer, simulating the reality and solving it numerically. So those are the three pillars of in quest of knowledge. And just to pinpoint one aspect of computation and why is that important, I'm going to throw in a joke. So there's three women, a physicist, an engineer, and a computer scientist, and they're traveling in a car. And suddenly the car starts to smoke, and it stops. And all three of them offer a solution to the problem. So first one is the physicist, and she says, well, this is obviously a classic problem of torque, and it has been overloaded beyond the elasticity limit of the main axis, and that's that. We're not going any further. So that's an explanation, but they're not going to do anything about it. Engineer says, well, let's be serious here. The matter is that there's a burnt spark in there connecting the rod, and I can easily, quickly go in and repair it. So engineer is a doer. Okay? And computer scientist says, well, how about we just get off the car, wait a minute, and then get in and try again. So there's this reboot your computer solution that is pointing to something in science that it's a simulated world and you can kind of repeat it. And that's actually the repeatability is sort of the key in computation. You can restart the system and try again, which in reality might not be possible. And that's one of the benefits of computation. So if you recall, well, we have these different objectives in science and engineering. So basically that physicist, she just wanted to pinpoint the problem and explain. That's basically explaining the fundamentals. but then you have to apply that knowledge and do something about it. So that's the basic difference between science and engineering. And the tools that you can use to do that is you can have theory, you can have the actual, so there's Albert Einstein as the face of theory. You can actually set up a lab setup or lab experiments to study whatever it is that you're interested in studying. This is just one example. Or I can set up a computation. This is actually discretization of a reservoir with a number of wells, and I can try to solve a problem with those three. And basically this course will start in a very mild way to introduce you into computation. And as you go through classes in this, so we will not necessarily do reservoir simulation in this class, but we will lay out the fundamentals so you can actually operate well in reservoir simulation class. You will also have some use of what we learned here in Introduction to Geostatistics, all of the reservoir simulation, and some other faculty in this course, in this building might decide to use different computational tools, but you should gain some basic understanding about how those computational tools are working, even if they're not MATLAB and you're not programming necessarily yourself. But also I invite you, as you go out through other classes, to do, for instance, like well logging and all of those, you could actually set up and do things yourself in MATLAB and use the tools that we introduced here. With nothing to analyze and plot the results very efficiently. Okay. All right. So what is a numerical method? I actually introduced that a little last time around. But basically, that's any time when we have a problem that doesn't have a formula, a given closed formula that is derived theoretically as a solution. That's when we actually need to go and use different methods to actually find that solution or search for it. And numerical methods are such methods. So basically, one designs an algorithm and programs a computer to try to solve that method. So every time you're actually solving a problem like that, computational, let's say that I have a flight of this airplane, I will take a domain, I will split that domain in a number of points, and I will search for a solution at all points, at every point. So I will not have super continuous solution at every point I could possibly imagine, which I get when I have a formula, but I will have sort of a discrete solution at the number, and that's called discretization. And basically, even if I look at this screen, it's actually pixelated. So anything that you have nowadays, we have better and better resolution of our screens, so things look amazingly continuous, but if you actually zoom into the pixels of your screen, you will see sort of that you have like little pixels, little squares of different colors, so ultimately that's you have that one solution or one color at one point, and that's what numerical methods are searching for. What is the color of that point? What is the number that I associated with that point? Even when whether I discretize very finely or coarsely, it doesn't matter. So it do depend on how do I discretize my problem and then solve for it. But basically, numerical solution will then give me a solution as an array of numbers or a matrix of numbers, which is the motivation for us to first figure out how to handle matrices, and linear algebra basically handles matrices, and we will overview linear algebra. So we need this first theoretical part that we will start on dealing with on Monday. We basically needed to know how to deal with all of these arrays that numerical methods use. Okay? And they could be matrices like this, they could be vectors, or they could be three-dimensional matrices, so I could have a box of numbers as well. Now, the benefit of computation, once I actually set up the problem and it's working, okay, and let's say that I'm doing a flood, like water flood, and for water flood I need to have a pressure gradient, okay, and I'm wondering how things change with the viscosity. I might actually spike that water with some polymers, so I might have different viscosity. Okay? So I might have different viscosities and different pressures or pressure gradients that I want to test. How are things working, or how are things displacing in my reservoir as I change those? The benefit of computation is that I'm going to set up my viscosity and pressure gradient to be what I want them to be, do a simulation, see what I need to quantify, what I need to do, typically a residual saturation of oil. And then I'm going to change it and do it again, and then change it and do it again. And there's this repeatability. Once I actually have a working code, I can keep doing it. And once the code is working, pressing a button on your computer is a little easier than actually setting up a new core, cleaning the core, setting up a new core in your lab, changing all of the things, and doing it all over again. So, a philosophical question for you. If I have a very good code that basically simulates how I displace oil with water in any kind of geometry, core or field, whatever it is, does that mean that I can throw away experiments completely? Why not?
There might be errors in the experiment that MATLAB can simulate.
And the other way around. So each of those, beware of anybody saying that, oh, with a click of a button you can get rid of something else. Typically for science to move forward, we need everything. We need experiments, we need computation, we need theory. All of those three have their own limitations, and there are limitations in different ways. So basically by comparing the three, we will actually find out, because there are certain things in experiment, I can do the experiment, but no matter what, I can't see inside the core. I see the pressure on one end, I see the pressure on the other end, I can do the mass balance and figure out what's the overall saturation in the entire core, but I don't see the details within the core. Where is the saturation higher, where is it smaller, depending on how permeable the core is. Whereas when I set up the problem numerically, I can actually see the details of the permeability field through my core. I can see the details of the saturation through my core that can possibly explain what's going on in the experiment. So there is this comparison that goes on. Now that said, in my numerical method, I have made certain simplifying assumptions. And those could bite me. Maybe things are not as applicable. So I always need sort of experiment to tell me, okay, you're good here, you're not so good here. So there's this dance in comparison between the two. So we need both. Okay. All right. Now let's actually come up with the method and implement it. And we're actually going to hint at how parallel computers are working here. So what we're going to do is we're going to sum up some numbers here in the class, okay? And do it in a table, and I will assume that all of you are in a table of numbers. So first thing, everybody think of a number between 0 and 5 and write it down. Or remember it, but it's useful to write it down. You did that? Everybody has their number? Please don't all be zeros. All right. So now in each row, we will start from your left. So the leftmost person, wherever you are, okay? You're going to tell your number to the person to the right, okay? And you will do a little bit of computation. You will add your number and his number, and then that sum you will pass along. And we'll keep going. Happy computing, let's go. So start well, it's very easy where we have only 2 people, but it's going to be a little more complicated over here. So remember, I meant whole number, let's do 20.3. Whole numbers, please. 0, 1, 2, 3, 4, 5, make it simple. Huh? So the person here, remember the sum, And then the rightmost person in each row will pass the number to the rightmost person here. You will do the computations, the same thing, and pass your sum down, and then he will tell us the ultimate result. $71 is the total. So what did we have at play here? I came up with a way to sum up all of the numbers here. Is this the only way to do that? No. There's multiple ways. We could have gone by columns and so forth, right? So there's multiple. What I designed is an algorithm. I can very easily see that this algorithm should give me good result in case everybody did the correct computation, okay? So we can also immediately see sources of error. Okay? And we can also see that something called loading, that different rows have different amount of work. So the gentlemen in the top row, they were done really quickly. It was only 2 of them, right? Over here, it was a little longer because we had more people. So they were actually kind of waiting for everybody else to finish. This is actually the fundamental. We will not go into parallel computation, but these days, most of your computers, they're called flood core, dual core, and so forth, meaning that they have 2, 4, or 8 cores, individual workers working together. So actually, those workers can individually do some tasks. So you will open Word with one core and MATLAB with another, so both will run efficiently. Here we had computation done in parallel, so everybody did a little bit of computation instead of me walking down and asking, what is the number? What is the number? Add them up. What is the number? Add them up. What is the number? Add them up. It would take me a long time to pass through all of you here and do the computation. That would be what one core would do, one processor would do. What we did here is processing in parallel, and that's the basically of effective computation down the line. So we did some algorithms. We saw some sources of errors as well. This is the algorithm. So there are some human errors here involved in memorizing the number. Now I chose very simple numbers, 0 to 5. If I asked you for some real numbers that had a lot of decimal points, we'd be in trouble. Adding those up would be a little difficult as well. So basically there's error in this summation. Each processor could make some error. And then depending on the number, they might not store it properly. They might not memorize it properly because humans are kind of flawed in terms of computation. These are the things where computers will definitely perform best, but they won't be perfect either. Because for storing number, I cannot store a number that has infinite number like number p or pi. It has, I often refer to it as p, which is in Greek, or pi, so you'll hear both from me. So pi has infinite number of decimal places, and those I cannot store in a computer all of them. So I have to chop it somewhere. So if every number in the number representation, if every number I chop a little, okay, then I will introduce error that piles up, and that's sort of numerical error that is inherent there. Needless to say, computers, even with that limitations, are definitely better than people. Okay? So those errors that we have in computers, they're typically easier to predict, and they can be actually analyzed, as opposed to analyzing human error. I don't know that we can go very far. Okay? It's a little random. All right. So now let's actually move on. So this is just introducing computation and its relevance. And now I'll actually do a couple of examples where we need numerical methods for practical problems. So if you imagine, I already mentioned the quadratic equation. Finding roots of that equation means finding x, and we know that we have 2 possibilities that will make this equation be equal to 0. Okay? So for this equation, I know actually I have a formula, and I will get an exact result if I just plug in the numbers. So basically 1 and 3 are solutions. Well, this is a simple equation, okay? Now, I also have a very simple law, so let's move on to something a little more physical. I have an ideal gas law, right, that basically relates pressure, molar volume, and temperature. R is, of course, a constant. Okay? So if I, for instance, have temperature and I want to find pressure and volume, I see how they relate together. Okay? Now, I might be wondering, so this is an easy one, but I might have actually a much more complicated, this is called equation of state. So if I actually go to one that describes realistic fluids, and we are very unlikely to find any ideal fluids at 3 kilometers down in a wellbore. Okay? They're not ideal, and they're not at any mild pressures and temperatures. They're not behaving nicely. So we actually have to describe it a little more realistically, and in your fluids class, which some of you are taking, as well as in thermodynamics, you will use Pegg-Robinson. So Pegg-Robinson has certain parameters that have to be tuned to the gas that you want to deal with, and those numbers are typically tabulated. I can find them, and I know what, I can just say that I know what my A and B are for methane. And let's say that I'm interested in temperature of 50 bars, in pressure of 50 bars and temperature of 473 K. Then I have actually, if I'm wondering, what is my volume that solves this equation for this pressure and this temperature? Do I know? Is it easy to find? If I'm wondering which volume satisfies this equation given temperature, so pressure is given, R is given, T is given, B is given, A is given. All I need to find is V. So I need to figure out what is the volume I have. I know what the volume is, for instance, of the surface. I need to figure out what is it going to be down the hole. Okay. This is something I would use, but I can't solve this easily. I don't have a formula that just spits out the perfect solution. So I need to design a numerical method. Now, what would be sort of a guess? How would you go about it? Let's say that you don't have a numerical method. Yeah. So one thing that when we're gonna formulate. So this is the first hint. We're gonna formulate the problem as a root or a zero of an equation. So I'm asking which equation. So if I put pressure as 50 minus what I have here on the left-hand side, it has to be 0 for the volume that I'm looking for, right? If my volume satisfies this equation, then pressure minus this has to be 0, and that's my function. So I'm looking for a root of this function. Yes?
That's how we solve it.
So this is the first step. This is just setting it up. And now I set it up actually in a classical way. I'm looking for a root of an equation, so I can apply methods that are already available. So that's often the first step in setting things up. So one thing is that I could do a guess. I could just guess. Start with an initial guess and evaluate how close this is to 0. And depending on how close things are, I can try to increase it or decrease it. And kind of, so that's called brute force search. That's not a numerical method. Okay. And then just keep going. Right? So one good guess is that simpler law, ideal gas law. So there I can just say VI is RT over P. So I can plug that in as a first guess. And then I kind of keep going and try to narrow down a solution. So that's a good first guess. And then I can actually see, well, what is my F evaluated for this VI, and it's about 1.87. Then I decide to go a little lower, okay? And I see that I'm negative if I actually plug that in. Now this is already cool. I have a function, and I have a negative value and a positive value. Must be that wherever I have a 0 is somewhere in between these two. Yeah? So I'm going to try 768. And I'm going to get positive, a little closer to 0 than 1.87. And you can kind of keep going. So basically, in between these two, I'm going to find the next one. Okay. And I'm gonna, in between this one and this one, which is 750 and 759, I'm gonna throw in a guess that is right in between and try. And I can say, okay, this is pretty close to 0. If I had a computer to do this for me, I could keep going, actually, and narrow down the solution. So you can actually easily program computer to say, try something, okay, evaluate it, or give yourself 2 values where you have a positive and negative value, and then take a half of that interval, okay, then find the next interval that is positive and negative value, take a half, and keep going until you zero in on the solution. This is actually the method that we're going to program down later this semester. I could have just plotted the function as a function of b. And basically then I just see where it intersects to 0. So this is a graphical way of solving this problem. Boom, it's somewhere here. I could zoom in to try to find, and it's approximately 755. If I need to be more exact than just this approximately 755, then of course I need to program and actually get a proper value. Okay. Now let's give an example for differentiation. We all know that derivative is the slope of the line, and that slope is tangent to whatever curve that I have. Okay. And you went through calculus, you got all kinds of rules of how do you do a different derivative of a function, right? And those are tabulated. You give a function, you know, you can find it. So basically, how would I approach this if I wanted to do find dy dx at x is equal to 1? What is the derivative?
2x minus 1.
Okay, so those are the rules that I'm talking about. So 2x minus 4 evaluated at 1 is, there we go. So you had a formula here to do that, right? Now, so that's basically the result. Now, what if this function was not given by a formula? So one example is, everybody knows what well logging is. So well logging, any kind of well logging, let's say neutron porosity, records a value for porosity at various depths along the well. So technically, if I plot that value, we typically plot it vertically, but essentially if I have depths and I have values, I have a function. What if I want to take a derivative of that? Do I have a formula? Not this kind, right? So I need to find a numerical way to do that. And that's why actually remembering that derivative is just the slope of a curve, whatever the curve is, kind of helps. Okay, so you can go back to that, that definition and find it numerically. So here, basically, whatever the curve is, this is a little smoother curve than a neutron porosity log would look like, but okay, bear with me. So essentially, if I wanted to find the derivative, I would find the slope. And for this slope, I know that I can basically find the slope. All I need is a value here, y value here, minus y value here, divided by the difference in x values, and that would give me an approximate derivative at the point that I'm looking at. So that is a numerical way to find the derivative. And that works for any kind of possibly ugly data that you have. Okay. Now we also have integration. Okay. So integral, we know, is area under the curve if I actually plot a function. So if I have this, I'm going to stick with this quadratic equation. If I gave you this, you would know how to find this integral, right? Again, you have analytical methods to integrate, especially simple polynomials. Those you don't even have to look up in the tables. So basically, you would go and find the integral, plug in the bounds, and find that this is 4/3. Now again, I might have a fairly ugly function. It could be a function that comes actually from plotting the data. It could be simply a function that is much more complicated than this, so I don't know how to integrate it right off the bat. Okay. So what do I do? How do I actually integrate? Okay. So if I'm looking for sort of an approximate method to integrate, I will plot my function, here's the function, and then I will place the boxes. So here, at this point, I'm going to draw a box, so there's going to have a constant value that I find right here. Actually, let me, apparently I'm not as tall as I think I am. So here's this value. I'm just going to extend it for the length of this box. So here I have a box, okay? And I know what the area of a box is, right? It's the height times width. Then at this point, I draw another box. Here's a box. I know its area. Then I find this box. I know its area. And here at this point, again, I take the value here, I just extend it further, and I find the box. So if I sum up areas of all of these boxes, did I find the area under the curve? No. I went a little above. So this is essentially this part here, the extra parts, this part, this part, this part, and this part. They're the extra, they're the error I'm making. Okay. But what can I do with these boxes? How can I make this more accurate? Smaller box. Okay. And then a smaller box, and then a smaller box. And I'm hoping in that process that I'm going to get more and more and more accurate. So let's check. So basically in numerical methods, I do actually have to verify. So I come up, I just kept what we described is actually an algorithm. Pick your width of a box, okay? And just draw these boxes and just sum up their areas. That's going to be an approximation to your integral. But I have to prove that as my width of the boxes becomes smaller, then I'm going to get more and more accurate. So that's something that we actually have to have a proof for. But when it works, it actually works nicely. So here, this is my smaller boxes. And actually, if I did this outside, so basically if I had 4 of those rectangles, the area would be 1.72. If I had 10, the area would be 1.44850 and so forth. 100, 1.3484. Million would give me 1.3333, and to this 4 decimal places, I actually cannot find the difference between this number and 4/3. So up to the 4 decimal places, this is as accurate as I'll get. If I do have an error, it's below here somewhere, so it's much smaller than the number itself. So in this case, this is called convergence. My method converged and actually gave me the result. The thing is, can I do million boxes by hand? I can. I would kind of grow old while doing it, right? So basically, this is where computers again come in handy because we can easily compute, and it's a split second for a computer to do that. Okay. So again, I already hinted, computers basically can speed up the process, and they can actually get very close to a pretty good result, as far as I actually care. So how do I actually decide whether, so here I had this, can I actually say that 100 rectangles, that this is actually close enough to 4/3? I could. Okay. So it depends on me. Now in a practical situation, you will have to figure out how close you want to get in your solution. And that depends on the practical situation. So let's say that you're traveling from Austin to San Antonio, and you need some gas. For all practical purposes, what's sort of the accuracy in terms of the mileage that you need to know between Austin and San Antonio? Right. Is it even up to a mile is just fine enough because you need to know, you just need to estimate how much gas do you need to have in your tank, right? Or Austin to Houston is maybe a little more. You might not have enough in your tank to go to Houston. So there's 160 miles. That's good enough for your basically decision on how much gas to buy. So basically, how close you need to be to the precise value, whether it's 160.7348, doesn't really matter. For the practical purpose of buying gas, you have enough gas for a drive. Okay? So in that sense, you are basically typically put in how close you want to get. Sometimes computational software does that for you, and you have to be aware of that, and I hope to bring that awareness, because later on, you'll kind of use software, and there's a tendency just to, oh, this result is correct because software said so, okay? Because internet said so, because computers said so. It doesn't really, there is certain inherent error that you have to be aware of, and basically software is making a decision for you, but you have to figure out if you're close enough. So again, how close is close? You decide based on the decision you need to make. Okay. Now again, computers can solve problems a lot faster, and we will actually learn how to do some basic programming to actually set the computers up to solve problems numerically, such as the 3 examples I gave. And again, programming, MATLAB or otherwise, is not hard. It requires practice, but there's plenty of help here. We will have TAs always helping out in the class. There is a lot of office hours, and the rest is practice. So we will start with some linear algebra review on Monday. Oh, this is 2 minutes. These movies are a little larger. So I'm gonna post this for you or send them via Canvas. Do please watch them. There are 2 interviews with Dr. Baumer and Dr. Lake, who remember how computing looked like when programs had to be, instead of being typed in, punched on punch cards. So you had like a card with a bunch of holes, and then you gave that to the computer would interpret it and kind of give back the result. It was a different time, it wasn't that long ago, and in those 2 interviews I'm going to actually show you that they're every time I'm really bummed about finding a bug in my code, and like I'm trying to look for it and I'm frustrated, and I remember, well, this is still better than punch cards. So it's good to have the perspective. So I'm going to post these movies, please watch them over the weekend, and see you on Monday.
About missing a class.
Uh-huh.
There's going to be an SPE conference on February 4th to 6th, so the 5th is a Friday.
So just
what time-
email me. Yeah.
Thank
I
you.
can easily verify that you went.
Yeah.
So,
Okay, so we can just email you for
Yeah.
symposium?
Yeah.
Okay.
and I will post the movie
Okay.
or video of the lecture, and you're required to catch up.
Yeah.
Okay.
All right.
Okay.
Thank you.
Mhm.